Hi, I'm Ryan Baker, and this is Big Day in Education. Today we're going to wrap up our week on knowledge inference with a discussion of memory algorithms. So up until this point, we've been talking about predicting future correctness. But is future correctness enough? What if you forget about it tomorrow? What if you know it today and you can show it again in 5 minutes, but tomorrow you'll never remember it anymore? So another way to look at knowledge is, how long are you going to remember it? This is relevant for all knowledge, but it's mostly been studied in the context of memory for facts rather than skills. Things like, how do you say banana in Spanish?
Banana.
What is the capital of New York?
Albany.
And where are the islands of Langerhans?
And your Patriots.
Now, it's long been known that spaced practice, or in other words, pausing between studying the same fact, is better than mass practice, aka cramming for an exam. So if you're cramming for your exams in grad school, don't do that. Practice over time. Early adaptive systems, like Leitner's flashcards, implemented this behavior in simple ways. We start our discussion of algorithms for modeling memory with the ACT-R memory equations. It didn't actually start here. There were people working on this problem prior to this, but we'll start here just for the sake of not going back to Ebbinghaus in the 30s. In Pavlik and Anderson's ACT-R memory equations, memory duration can be understood in terms of memory strength, which is sometimes referred to as activation. The formula for the probability of remembering an ACT-R is based on 3 parameters. M, the activation strength of the current fact. Tau, the threshold parameter for how hard it is to remember. And S, the noise parameter for how sensitive the memory is to changes in activation. In other words, when you re-encounter a fact, how much better does your memory get? And you should note here, by the way, a logistic function like PFA from a couple lectures ago. Now mind you, that's not because this was building off PFA, it's because PFA was building off of this. But that's neither here nor there. The formula for the activation is represented by this formula, where we have a sequence of n cases where the learner encountered the fact. And each t of I represents how long ago the learner encountered the fact for the ith time, how many seconds ago it was. And the decay parameter d represents the speed of forgetting under exponential decay. So in other words, based on the parameters of this model, we can kind of infer how much will your memory decay over time, how rapidly will it decay over time. There's a couple implications to the ACT-R memory equations. First, more practice equals better memory. That's an implication here. And it's kind of true in the real world. You're probably more likely to remember something if you encounter it more. Also, more time between practices equals better memory. That's true of almost all the memory models. But one kind of interesting implication of Pavlik and Anderson's model is that the most efficient learning comes from dense practice followed by expanding amounts of time in between practices. Now one thing that's kind of cool about this is exactly what Leitner was doing in his system back in the 70s. A more recent competitor to ACT-R's memory equations is MCM by Moser and his colleagues. This model postulates that the decay speed drops the more times a fact's encountered. So in ACT-R, the decay speed is constant whether you've encountered something 1 time or 1,000,000 times. But in MCM, the more times you've encountered a fact, the slower it is to decay. MCM is represented by a functionally complex model where knowledge strength, and therefore the probability of remembering, is a function of the sum of the trace's actual contributions divided by the product of their potential contributions. And a power function is estimated as a combination of exponential functions. Each encounter with the knowledge has an exponential function for decay, but it turns out to sum up to a power function. And building on that, Moser and Lindsay introduced the DASH framework, which extends previous approaches to also include item difficulty and latent student ability. DASH has got a neat feature. It can use either MCM or ACT-R or other frameworks as its internal representation of how memory decays over time. So whether or not you like ACT-R or MCM better, you can use DASH to also include item difficulty and latent student ability in your estimate of student forgetting and memory over time. Also very recently, Duolingo, you've probably heard of it, like 6 million people have used it to learn a language, fits a regression model to predict both the recall and the estimated half-life of memory based on the lag time. It's based on an estimate of the exponential decay of memory. But Duolingo does this calculation not based on the kind of complex algorithms that are recursive or iterative in nature, like seen in Pavlik or Moser, but instead uses a feature set including the time since the word last seen, total number of times the student's seen the word, total number of times the students correctly recalled the word or failed to recall the word, and the word difficulty. So it tries to capture some of the same ideas as Dash in a formulation that is quicker to implement, quicker to run in real time.
It's worth also mentioning another key memory phenomenon, which is spreading activation, where encountering or recalling something in memory also increases the memory activation of related concepts, facts, or ideas. And there hasn't been very much work on this in our field, but Ma et al. 2023 do build a DKT family algorithm for memory that uses associations between items right along these lines. Well, so this wraps up our knowledge tracing week. Up next, relationship mining. I'll see you next week. Thank you. This is Ryan Baker, Big Data in Education.